Okay, so welcome back to Applied Machine Learning. This is the start of week 3, and in this week we'll be talking about extensions and variations of Perceptron with the hope that you can apply Perceptron onto real data set and to do real classification in kind of real life scenarios. So remember that we had provided all the theoretical kind of foundations of Perceptron. How the algorithm works in testing time, in training time, its convergence properties, when it will converge, how fast it will converge, right? What to do if it does not converge, right? All those theoretical materials will be applied for the first time to a real data set. That's your task in homework 1, which is a real kind of a data set that, similar to those that you will do in a Kaggle competition or later on in your life, in your work after you graduate from this program. So here's a quote from Grace Hopper, one of the most important, influential computer pioneers. She said that a ship in port is safe, but that's not what ships are made for. Okay, so that's exactly the case of Perceptron. We dealt with the theoretical properties, which was very beautiful back in week 2, but that's not what perceptrons were made for. Perceptrons were made for real problems like image classification, right, text recognition, those kind of real machine learning problems. So that means it's actually much harder than what the theory says. You have to deal with real data. Before that, here's an interesting trivia about Grace Hopper, the computer pioneer, and one of the most influential female computer scientists. So she was associated with the discovery of the first computer bug in 1947. Even though this term bug was not invented by Hopper, but rather coined by Thomas Edison back in the 19th century. And by the time of the war, Second World War has been widely used by many fields of engineering, and Grace Hopper was working on a computer, one of the first computers, by the way. So if you remember, the first kind of general purpose large scale electronic computer was made in 1946, right? Just 1 year after the war, after the end of World War II. It was started during the war, of course. It was a war project. And ENIAC was dedicated in early 1946 at the University of Pennsylvania. 1 year later, in Harvard, they were making a new computer, designing a new one, and Hopper was part of the team which discovered the first bug, which is actually a moth stuck on the relay. So here's the real log, and actually the moth is here, right? And the text says the first actual case of a bug being found, right? And this piece of paper, along with the moth, can still be found in Washington, D.C. if you go to the Smithsonian National Museum. And I kind of highly encourage you to look at those. I did not have a chance to look at it, but I think it will be very interesting. So Grace Hopper, because of her legacy in computing, now there is a conference called Anita Borg Institute, Women in kind of Transforming Technology, or Women in Computing, celebrating women in computing. And this conference is happening every single year, and I highly encourage you to go to those conferences. Okay, so back in week 3, we'll be doing Perceptron in practice, and we have kind of looked at many problems with the kind of vanilla Perceptron. For example, it does not converge with inseparable data, and in reality, almost every single data set is not separable, or at least not trivially separable, with any reasonable feature map. So you have to do something about it. And updates might often be too bold, that means too big. That kind of is not very stable, and one of the major problems with Perceptron is that it does not optimize margin. It's totally happy with any non-zero margin, right? It does not kind of maximize the margin or optimize the margin, which SVM, support vector machine, would do in the next week. And its result or output is sensitive to the order of examples. Okay, so we'll be presenting different ways to alleviate these problems without going all the way to kind of more sophisticated methods like SVM or kernels, which will be the topics of the next 2 weeks. But for now, we'll be using very simple tricks, very kind of easy methods to kind of alternate the perceptron a little bit. Just adding a few lines of code, maybe 1 or 2 lines in Perceptron pseudocode, which is very, very simple, and you can make it work much, much better, and almost to the same kind of accuracy with an SVM, but much simpler and much faster. Okay, so part 2 will be devoted to voted perceptron and average perceptron, which is very, very useful. And as you know, vanilla perceptron is not very useful in practice at all. And average perceptron kind of totally revived the concept of perceptron and made it a lot more useful in practice. And part 3, we'll be talking about another variation called Myra, which is inspired by perceptron, but it's almost kind of in between perceptron and SVM, right? It's kind of an intermediate step between perceptron and SVM. It's called margin-infused relaxation algorithm. It's also kind of maximizing margin in one example, or online SVM, sorry. And part 4 will be looking at practical tricks and how do you do those tricks on homework 1. We'll be looking at homework 1 data sets. It's training data, it's dev set, and it's test data. And homework 1 is working on a very, very interesting data set, which is called adult income, which basically tries to classify an adult to be positive or negative. Positive meaning he or she earns more than 50K a year, and negative means he or she earns less than that, less than 50K a year. And the input features are the person's age, education level, kind of work sector, occupation, race, gender, and country of origin. Like these features, like in a census, right? And then you have to decide whether this person is more likely or not to earn more than 50K, right? It's a very interesting data set. And part 5, the last part, is kind of an optional module, which will be talking about logistic regression, which is deeply connected to perceptron, very similar to perceptron, but just softer. So perceptron can be viewed as a hard version of logistic regression, and logistic regression can be viewed as a kind of soft version of perceptron. Now, just to recap what we had in week 2, we talked about a perceptron learning algorithm, very simple algorithm, just goes through data until it converges, and every single time you made a mistake, you do an update, and the update is basically like added to the weight vector if it's a positive example, otherwise you kind of subtract it from the weight vector. So after a few updates, you're bound to converge, and this convergence bound is very small. It's r squared over delta squared. R is the radius of the data set, and delta is, this part is kind of a safety net, is the safety buffer. Right. So this is the picture of the convergence property and the convergence proof from week 2. And this week we'll not be dealing with these kind of mathematical proofs. We'll be dealing with more practical stuff, right? And we spent a lot of time last week talking about the idealized machine learning versus the actual view of machine learning. The idealized view of machine learning, it kind of views machine learning as automating automation. Like you just need to feed the algorithm with input and output pairs, and it will automatically output a model. That's totally not true. The actual form of machine learning, which is happening today in industry, is that you have to supply a feature map as well. Okay, so no data would come in as a vector. Like you can give me an image is not a vector. You can give me a sentence is not a vector. You can give me a person, and he comes with a few features, but that's not a vector either, right? So you have to kind of pre-process this data into a vector form, and to do that, you have to define a feature map yourself. And we have talked about feature map a lot last week. So this is the actual form of machine learning. You have to kind of hand engineer a feature map, okay? And the performance or accuracy of your learning algorithm largely depends on the feature map. Right, so the modern version of machine learning, the kind of cutting edge area in machine learning is called deep learning, which is also known as representation learning, where you try to automate this feature map learning as well. So you don't want to define the feature map yourself. You want the machine learning algorithm to figure it out automatically. So this is why we say deep learning is automation, or automation to the power of 3, right? But that will be the topic of another course. So we'll be only spending 1 week, the last week, week 10, to give you some flavor of deep learning. But this course is by no means kind of focusing on deep learning at all, because you have to understand the basic components of machine learning first before you can kind of study deep learning, right? Now, some Python demo, which I promised. So I wrote a Python program, and it's here. So you can see that it kind of randomly generates a data set into positive and negative classes, 2 classes, and then it runs Perceptron algorithm until convergence. And I made sure it's separable for sure, otherwise it will not finish, right? And as you can see, Perceptron does not optimize margin at all. Its margin is often very, very small. It's very, very close to one of the data points, which means it's kind of not very safe, right? So at testing time, if there's another point here or here, which should be belonging to this class, but according to this line, this separating boundary, you would classify it to blue, right? This is another example, and it's even worse, right? So it will be not very safe around this area, right? Right? Margin is very, very small. Margin is very, very small. Margin is very, very small. Yeah, again, margin is very, very small, and you would rather want kind of this line to be the separating boundary, which is much safer. But Perceptron doesn't do that. Perceptron, again, is perfectly happy if you can classify every data point. And how well does it classify? I mean, how much margin does it give? Doesn't matter. That's not my consideration. So that's Perceptron. And if you compare it with SVM, which we'll talk about next week, right? SVM optimized margin. Right? SVM optimized margin. SVM optimized margin. And the circled data points are called support vectors, which we'll talk about next week. All right, Perceptron does not optimize margin, SVM does. Okay, very clearly, right? SVM is this line, bold line, and Perceptron is this line. So clearly, this bold line is much better.